Hello everyone, welcome back to module 3 session 4, continuation of the session 3. Here session 4 in the whole module 3 consists of the operational amplifier, where the whole syllabus consists of the introduction to operational amplifier, the various operational amplifier input modes, op-amp parameters such as CMRR, input offset current, input offset voltage, and input bias current, input and output impedance, slew rate, unity gain UBW, that is unity gain bandwidth product, and distortion parameters like TTH, that is total harmonic distortion, and transient response, etc. we have seen in session 3. Continuation of that is your session 4 continuation of, and the op-amp parameters are still continued here, where you have the input impedance, and here you have differential input impedance and common mode input impedance. Next input offset voltage, output impedance, slew rate, and references. Of course you have learned about the slew rate, just a definition. Here you will be little in depth, little bit detail about the equation and the graphical procedure, and the different text or the Google websites which you have referred is under references. Finally, the self-test of 10 questions where the answers are given at the end of the session. Input impedance, it is defined as the impedance seen by the input. Input means inverting or non-inverting input, both it can be, or anyone it can be, depending on the type of the input you are going to use. Applied to one input terminal where the other input terminal is connected to the ground. Here, if one input terminal is given, the other input terminal is connected to the ground, then it is called as single mode. Okay, single mode input. Typically, the value of the input impedance, that is Ri, is approximately equal to 2 mega ohm. In here, the two basic ways of specifying the input impedance of an op-amp are the differential and the common mode. Then hence in the op-amp parameters, the two types of input impedances are differential input impedance and common mode input common mode input impedance. Okay, the common mode input impedance, it is the resistance between each of the input. Here the resistor is been connected between each of the input and ground. See, this is inverting terminal, pin number 2, non-inverting terminal. In this pin, inverting and non-inverting terminal, even though the inputs are being given, there are two resistors which is connected to its respective terminals, and the common point between these two resistors are grounded, and that gives the common mode input impedance. Zin is the symbol to calculate the input impedance. The common mode input impedance is the resistance between each input, is a resistor which is being connected between each input and the ground. Here also between each input and the ground, and is measured by determining the change in bias current for a given change in common mode input voltage, which has been shown clearly in the figure. Okay, whereas the differential mode input impedance means here the total single resistor is present between the inverting and non-inverting inputs. This is your non-inverting input, this is your inverting input, and a single resistor is present in the in between the inverting and non-inverting. So it is the total resistance between the inverting and non-inverting input is called as differential input impedance. The common mode input impedance and the differential mode input impedance are clearly given in the figure here, and it is self-explanatory also. Next, another important parameter is input offset voltage. Input offset voltage here, ideally the two input bias currents are equal and the difference must be 0. But practically, this is ideal condition. But practically, however, the two currents will not be exactly equal and will not be 0 also. The input offset current, it is also called as IOS, I suffix OS, is the difference of the input bias currents expressed as like this. If I1 is the input current, I2 is the input current at inverting and non-inverting terminals, then it is IOS is equal to the difference between I1 and I2. Okay, this is the absolute value you have to calculate. It is not always I1 minus I2, it can be I2 minus I1 because we are going to calculate the exact value. And remember that since we are using this common mode input impedance, we are directly using the common mode input impedance to calculate the input offset current. Input offset current should be ideally 0 if there are no input, and ideally 0 at the output if there is no input. But practically it is not so. The difference, to calculate the difference, we are going to calculate the absolute value of the IOS, that is input offset current. Next, here before going into the output impedance, another parameter, actual magnitude of the offset current. Actual magnitude of the offset current are usually at least in an order of or 10 times less than that the bias currents. In many applications, the offset current can be neglected. However, high gain, high input impedance amplifiers should have as little of input offset current as possible, because the difference in current through large input resistance develops a substantial offset voltage, which is directly given in the diagram. It means that here effect of the input offset current is been clearly shown by this common mode connection. Okay. Next, another important parameter is the output impedance. In the output impedance, here the pin number 6 or the output terminal is here. From the output terminal, a resistor is connected and it is been the other end is been grounded. Likewise, you can calculate the output impedance capital Z0. It is defined as the impedance given by the output or the load for a particular applied input. The typical value is approximately equal to 75 ohms. Another important parameter already which we have discussed is the slew rate, but here I will just tell you how the slew rate has been measured. In the last session I just missed out this measurement of slew rate, so I just thought I will take up once again. Slew rate, as I told you, it's defined as the rate of change of output voltage per unit time, or it also can be defined as the maximum rate of change of an op-amp's output voltage and is given in units of volts per second. How abruptly the op-amp output change with respect to the input with the volts per microsecond time, that is called as a slew rate. So here, if this is the connection here and this is the input, at the output you just see the output is just shooting up and becomes constant. So the slew rate is del V out divided by del T. dV naught, or it is also called a dV naught by D, differential output voltage with respect to time, is expressed in volts per microsecond. So capital S is equal to dV naught by dt, or capital S or SR is equal to del V out divided by del T. So ideally the slew rate should be as high as possible. We have seen it in the last time, but the typical value of the slew rate S is equal to 0.7 volt per microsecond. Okay, so slew rate is also the maximum rate of change of output voltage in response to a step input. So this is the step input. This is called as a step input, where there is a change of the voltage from 0 volts to the 1 volt is a slew rate of an op-amp. The slew rate is dependent upon the high frequency response of the amplifier stages within the op-amp. It is a measured, slew rate is measured with an op-amp connected as like this, as shown in this figure. This is the test circuit. This particular op-amp connection has a unity gain, because here we see that here the inverting is connected to the output, that is the unity gain, or the non-inverting configuration is being connected to this input Vin. This gives this type of connection. It gives the worst case or the lowest slew rate also we can calculate by this. So hence it is taken as a test circuit. The high frequency components of the voltage steps are contained in the rising edge, and that the upper critical frequency, okay, of an amplifier limits its response to a step input. So for the slope increases, here you see the slope increases as upper critical frequency decrease. This is the step input voltage and the resulting output voltage waveform. So likewise we can calculate the slew rate measurement, or you can see the slew rate measurement. These are the few op-amp parameters which has been continued from the last session. Coming to the references, as I told you, you can refer to any prescribed textbook or to any genuine Google, okay, or any search engine websites, okay, or any prescribed textbook or materials. Thank you. Hope the session was very interesting and clear. So see you once again. Okay, thank you.